Okay, folks, video's on. And it looks like a lot of us are staying home to do the exam today. So, small class. 11 people. All right. That means you guys get to ask a lot of questions and not feel like you're picking up somebody else's questions. Okay, so we stopped here and I said I don't want to talk about hemiacetals and acetals until next time, and this is next time. The picture up at the top here, I have no idea why it's like vitamin A and the chemistry of vision like that, how it got there, but let me write in what it should look like underneath that little yellow banner there. Pen on. Okay, so we got an oxygen here, and we've got the double bond like that. And it says acetal formation. There we go. Okay, so acetal formation, and we're starting with an aldehyde or a ketone there. So if it's the aldehyde, it's going to be the H, and if it's a ketone, it's going to be the R, symbolizing the rest of the molecule, and that's a hydrocarbon chain, also called an alkyl chain. Okay, so what we're doing with our hemiacetal and acetal formation is we're taking an alcohol, so you guys see how it's ROH right there? It's telling you an alcohol, doesn't matter if it's methanol, ethanol, propanol, whatever. And you've got H2SO4 up there, which is an acid catalyst. So sometimes you'll see H2SO4, sometimes you'll see H+, sometimes you'll see H3O+. We just have to kind of just know that that's an acid catalyst, helps us along. Okay, so what happens when we add an alcohol and acid catalyst to an aldehyde or a ketone? Well, the carbonyl group right there, the carbon double bond O, that's going to turn into COH, and the OR portion of the alcohol is going to attach itself right there, and the hydrogen portion of the alcohol takes off. Don't worry about where it goes. If you were to take Chem 12, we would have to know where it goes, but this is 2B, so we're just going to trust that it's there somewhere. We're just not interested in it, and yeah. Okay, so in this part right here, the OR appears right there, and the blue oxygen right there is this one right here. Are we okay with that, folks? Like what that looks like, what's going on there? No answer. Okay, so the H that's right here, that appears right here, and the R in green is right there. Okie dokie smokies? Kind of, sort of, maybe? Okay, now that is the hemiacetal. And hemi here, it means half, like hemisphere, it's halfway there. And then if we add another alcohol to this, so we have another ROH right there, what happens is we see the disappearance of the OH, and in its place we have the OR there. And they indicated that the R here can be the same or different than the R here by putting a little prime there for you guys, just to distinguish between the R's, and they color-coded it for you. Yay! So hemiacetal, we've got a single OR on there, and the acetal, we have 2 ORs on there. Now, why on earth is this weird thing important? Well, it's important in sugar chemistry. So we're going to get there when we do the carbohydrates chapter, and you'll see why we learned hemiacetals and acetals. Any question at this point, folks? Yeah, go ahead.
So all these have to do with different types of varieties of glucose or sugar molecules, correct?
Yes, sugar chemistry, yes. Okay. So what is the general hemiacetal acetal look like? It's right there. And what does a general acetal look like? Right there. Are we all right with that, folks? Okay. You can also have cyclic hemiacetals, and whenever we have a cyclic structure, it always freaks us out. But unfortunately, we need to talk about the cyclic structures because this is important, again, in sugar chemistry, because the sugars will open up into a straight chain and they'll close back up into a cyclic structure. And that's pretty important. So right here, folks, let me draw in the carbon. Make it green right there, there, and there. That's this one right here. Okay? Now in the hemiacetal, you have bonded to the green carbon an OH and an OR. So the OH, folks, you can see in the hemiacetal is right there. And the OR portion of it, we have OR. So right there is the OR. It's just that it's attached at the back end to this carbon, so that freaks us out. But if you put your hand over it like this, you can see the OH and the OR right there. Are we all right with that? Kind of, sort of, maybe? Okay, so looking at this one right here, you can see the OH, right, folks?
Yes.
Okay, and then right here you have an O, and then the rest of this is just what? It's R. It just happens to be bonded to that green carbon on the back side, but you still have an OH and an OR bonded to that green carbon there. So those are both hemiacetals. They're cyclic hemiacetals. Questions for me? No? Okay, moving on then. So, like I said, this is important in sugar chemistry, and here is the milk sugar, lactose. And what we have is galactose and glucose. So this part is galactose, and this part over here is glucose. And lactose is a disaccharide, meaning that it has two monosaccharides bonded to each other. And the two monosaccharides that are bonded to each other are galactose and glucose. Okie dokie smokies? Okay, so where does the hemiacetal and the acetal appear? Well, let me draw this in for you folks, okay? So, right here where we have the acetal, I'm going to draw this blue carbon right there. And you see the two oxygens bonded to the blue carbon, folks? Okay. So on this side, if you go this way, and on this side, if you go this way, and you ignore the fact that it's a big old monster cyclic beast, what we can see is that this carbon right here is bonded to two O what's? Two ORs. You could have gone that way or this way, but anyways, it's bonded to two ORs there. And when you have that carbon bonded to two ORs, that's the acetal. If you have the carbon bonded to an OH and an OR, that's your what? Hemiacetal. Yep, so it's pointing to it right there. I'll put that one green. So your hemiacetal, you've got your OH, and then on the other side, you've got OR. Does that make sense, folks? Okay. And yes, you can keep on going if you want, this way or that way, but you've got OR over there. So you've got the hemiacetal right there. Are we okay with this, folks? Kind of, sort of, maybe? Okay, we will use this again, so that's the reason why we're going over this. Okay, so do some reactions. So in this reaction on the top, we have formaldehyde. So that's our smallest aldehyde, where it has an H on both sides. The rest of the aldehydes have an H on one side and an R on the other. Are we okay with that, folks? Okay, so formaldehyde is going to react with 2, and it says ETOH up there. That is ethanol. That's just a handy little way of writing ethanol that organic chemists love to use. ET is not some new element, so you don't have to worry about that. This right here is ethanol. Okay, and ethanol is CH3CH2OH. Now, if we are going to react our ethanols with our aldehyde right there, we might also want to recognize that ETOH is just a specific version of our general formula for alcohols, ROH. Are we all right with that? Okay, so ROH is the general formula for the alcohol. And ethanol right here, that's a specific alcohol. Okay, so the OR is going to add at the carbonyl carbon right there. So the carbonyl carbon, if you guys remember, is a carbon double bond oxygen. And it doesn't have the intermediate step where we stop at the hemiacetal. It just goes ahead and gives you the acetal product over there. Well, you have 2 of your ORs bonded to this carbon right here. So let me go ahead and draw the carbonyl carbon in blue. Right there and right there. And so right here you have RO, and I'll write this one backwards as OR, but it's the same thing. That blue carbon right there, the one that was a carbonyl carbon from the aldehyde, is now bonded to 2 oxygens that are connected to alpha groups, R groups. Okay? So this is the acetal product. Are you guys okay with that? Okay, now do you see why it's 2 ETOH? You're adding 2 of them? Okay, so I'm going to warn you that oftentimes what organic chemists do is they'll leave this number off like that, and they assume that you know that there is more than one ethanol molecule sitting in the reaction vessel. Whatever it is you're doing it in, a beaker or a flask or whatever, okay? So sometimes you just have to make that step of like, oh, I kind of remember her talking about that. Let me go find that slide. Oh, here it is. I wrote it down. I need to know that I need 2 of them. Now, looking at the reaction arrow, folks, above it, do you see the H+? Okay, so that's saying you have what in there also? When we have H+ or H3O+ or H2SO4, that's a what? Yes, it's an acid catalyst. Okay, so are we okay with the different parts of the reaction? Okay, sometimes you'll see the H2O, sometimes you won't. It just kind of depends on who writes it. Most of the time we see it when it's in a textbook or it's in this class, just because we like you guys to see what's going on. Questions for me? Okay, so notice how it says, was that a question back there or was that Okay, no one admits it. Okay, so where it says products are favored at equilibrium. So what's gonna happen is you're gonna take some of this and throw it into some ethanol, and whiz bam bang, the aldehyde and the ethanol and the catalysts are gonna get together and make some product babies over here. And it says products are favored at equilibrium. So you're gonna have a higher concentration over here of products than you had of reactants. But notice the arrow is double. That means that some of the reactants are kind of lazy and they're just like, no, we don't feel like reacting today. And so they'll just sit there. So you still have some of the reactants sitting around with the products when you get to the end of the reaction. So as students, we want all of A to react with all of B and give 100% C, but that's not reality most of the time. And if you notice in this double arrow right here that the top one is bigger than the bottom one, you guys notice that? Okay, it's saying to you that it's product favored. Like, it'll make quite a bit of product, but just not 100% product, and it'll make more product than you have reactant left over. Whereas in the bottom one it says reactants are favored at equilibrium. That means that you've got this, and you put them together with the acid catalyst, and they do a little bit of reaction and make a little bit of product, but these two are pretty lazy. They don't make a lot of product. So there's a lot of this sitting around when the reaction ends. So you got a little bit of product, a lot of reactants left over at equilibrium. So are we okay with the whole reactant favored, product favored thing? Okay, and notice on the arrows here that the backwards arrow is larger than the forwards arrow. So it's saying it makes a little bit of this, but we still have a lot of that sitting there. Okie dokie smokies? Kind of, sort of, maybe? Okay, so notice the difference here. We've got a ketone, and up there we have an aldehyde. The aldehydes, they tend to be product favored, whereas if you do this reaction with a ketone, it tends to be reactant favored. Now if you got two R groups down here, they kind of take up a lot of space, and it's hard for your different reactants to get into the carbonyl-carbon where the reaction is actually taking place, because the R groups take up a large space. Hydrogen is super small. So it's really easy for your ethanol, your acid to get right into that carbonyl-carbon right there, because it can get around that tiny little hydrogen there. Okay, folks? Questions for me? Concerns? Yeah, go ahead.
What if another element is added to it? Let's say, as you mentioned up there, like instead of EIOH, what if I kind of a part of H2O, I send a formula like glucose into the mix?
They just, what if you throw something random in there?
Yeah.
Well,
Will it be the same?
Well, it would matter what the random thing is.
Like glucose.
Glucose. I don't know that glucose would interfere a whole lot, because you're already at the acetal, hemiacetal product there. Maybe if you have something specific in mind, like you could email it to me or something, and we could talk about what would happen.
I'll put it in the worksheet once I see it.
Okay, okay, sounds good. Okay, folks, at the bottom, looking at that reaction right there, it kind of looks crazy, like you're making an alien. But you can do this. So, if you take a look at this, do we have an aldehyde or a ketone? In a ketone, you have carbonyl-carbon, and it's bonded to R on both sides. Put your hand over it if you need to ignore the fact that it's a cyclic structure. Are we okay with that? Okay, so you have an acid catalyst here, and you have an alcohol thrown in there. So if you have a ketone or an aldehyde and an alcohol and acid catalyst, is going to give you a hemiacetal or an acetal. And if we look at the alien over there, we might get scared, but we have to trust that we know how to do this because we've learned this. So anyways, when you have that situation, you're going to add OR and OR. This is a diol, so it's like two ROHs just connected to each other. So we can all see the OH, right, folks? Say yes.
Yes.
Yes, we can all see the OH over there. If I cover this up like that, can you see the ROH? So this is the R portion, and that's the OH. Okay, I'm going to do the same thing on the other side. Can you see the ROH here? Okay, so what we're going to have is something like this, except these R groups are connected to each other because of this connection right here. So what we're used to is something like that, where we have like CH3 and then OH, and we add two of them. But now they're connected. So what happens is that we do get the acetal, we do get the carbonyl-carbon bonded to OR and OR, except our ROH and our ROH over here are connected, so the OR and OR here are connected. So this right here is right here, and you can see that right there, and then that's bonded to the carbonyl carbon here. You guys kind of sort of see that? So you form two rings, which is kind of crazy because one ring freaks us out, right? And then you got two, and you're like, oh, I can't do that. Yes, you can. Yes, you can. Okay, so there are your carbons right there. Okay, so we can also go backwards. You can have an acetal and throw some water and an acid in there, and it's gonna go backwards, and it's gonna give you the ketone back, and it would also give you the alcohol back. So we could write plus this thing right here if we were going this way. Okay, folks? The whole two-way reaction thing, I know, is kind of confusing for us, but it happens. Okay, before I move on, questions? No? All right, let's do some problems, because we all love problems in chemistry, not in real life, right? Lots of problems. Okay, so we want to draw the missing reaction or product for the following three reactions here. Okay, folks, so we have an aldehyde, and we have an acid catalysis right there. And then you see how it says ETOH right there? So what we're assuming is you know that the aldehyde and the acid are sitting in ethanol. And ethanol is a liquid, that's our drinking alcohol. And so there's a lot more than just one molecule there. So remember how I said sometimes you won't see the two and you just kind of have to know?
Yes.
All right, oh, we got one yes. All right. Okay, so the ETOH, that right there, folks, is our ROH. So we've got those carbons like that. So I'm just gonna go ahead and draw the red portion. And then I'm gonna draw the blue portion. So we got the blue carbon right there. Okay, on that blue carbon, do I lose my hydrogen? This one right here. From what we've seen already, am I losing that hydrogen?
No, you don't.
No, it's still there. And what appears on that carbonyl carbon, folks? If we go all the way through to the acetal, that carbonyl carbon goes from carbon double bond oxygen to what? Oh, is that yours? Okay. I was like, it sounds like one of those Amber Alerts or something. Okay, so we have now carbon single bonded to two oxygens, and what is bonded to the other side of the oxygens?
Oh wait, R.
Your R group, yes. And what is our R group in this problem? It's ET, because you have ETOH right there. Ethanol is the alcohol, and ET is CH2CH3. Okay, so the ETOH is just a shorthand way of saying CH3CH2OH. Okie dokie smokies?
Yes.
Okay, so is anybody confused they need me to do that again? Are we all right with this? Kind of, sort of, maybe. Okay, excited crowd today, awesome. All right, number 2. We got electrosynthesis here. We're gonna work backwards. Alright, so I'm gonna erase my ethanol right there. And we've got our carbonyl carbon located right there. So you can see that you have OR here and you have OR right there. Are we okay with that, folks? Yeah? Okay, so working backwards, I'm gonna have 2 reactants. And what is my alcohol? It might already be there. Can you guys see that right there? So here, instead of doing plus 2CH3OH, and that is ROH, what they did is they wrote it there on top of the reaction arrows. So we actually don't need it here. You write it in one place or the other. Are we okay with that? All right. What is the other reactant, folks? What would I draw on my paper that's not going to change? Going from reactant to product or product to reactant? Yes, the cyclohexane. So the cyclohexane stays the same, and we're going to put the carbonyl carbon at the same spot. You could put it on the top. Just make sure you know what you're doing. And that blue C is going to be connected to what? Which atom? Yes, oxygen. Single, double, triple?
Double.
Yes, double bond. So we have cyclohexanone, and it's going to react with 2 methanols. And the OR is right here, folks, and that appears here and here, and right there it tells you that there's 2 of them. It will not always do that, okay? Sometimes it assumes that you know that there's more than one of them in there. And you would either put it here, or you could put it here, but you don't put it in both spots. Now notice how it wrote HCl catalyst down there instead of H+, or H3O+, or H2SO4, and it went ahead and told you it was a catalyst. So again, we're seeing a different way to write it. And it's underneath the arrow instead of on top. And yeah, there just isn't a whole lot of consistency with that, but we kind of expect you to just roll with it because it's chemistry, right? Yes. Okay, are we okay with this one? Kind of picking out the different pieces? All right, so let's do 2-pentanone. So is that an aldehyde or a ketone, folks? 2-pentanone, the one on the bottom. It's a ketone. It has the own ending, so it must be a ketone, right, folks? You have a carbonyl. Carbon is bonded to 2 different R groups right here. Now, notice this right here. Do we see the ROH here? Yes. Okay. And then on the other side, you have ROH. So this is a diol. So one side is going to connect to the carbonyl carbon, and the other side is going to do the same thing, and we're going to form a cyclic structure, which I know you guys hate, but that's the problem, so we're going to do it. All right, so I'm going to draw this guy and this guy in the same way. I'm going to put the black carbon up like that so you can see what we're doing. And this right here, I'm going to draw it in green. Okay, so the black carbon, the carbonyl carbon, when we form an acetal, you have OR and OR bonded to it. Are we okay with that? So usually we write OR and OR. Well, the thing is that our ORs are connected to each other. So we're gonna put an O and an O right there because we're okay with that, right? Yes, no, maybe so? Okay, and that's this oxygen and this oxygen. We can imagine it like that. That's not exactly how it goes with the mechanism, but we'll simplify it and put it like that. I'll show you guys the mechanism for it in another slide. But okay, the oxygen's there, and now you see we have 1, 2, 3 carbons there. So what we want to do is 1, 2, 3. So you've got CH2, 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 and that's those CH2s right there. Are we all right with this? Do you guys see that? Okay. And it's just because your R's are connected to each other. If you imagined it like that, where you had ROH and ROH, you could like do this, and you'd have OR and OR. Okie dokie smokies?
Yes.
Okay.
The round forms are the hexanol ring.
What?
On the carbon, specifically where it has 2 oxygens, it breaks down and forms a hexagon.
Yes, because you're attaching 2 oxygens to it, and the oxygens are linked in the back. I'll just give everyone who's still writing a minute to finish.
H2C.
We're good? Okay, anyone else still writing, folks? Okay. So now we're gonna go backwards. So we went forwards and we made hemiacetals and acetals. And now we're gonna go backwards and form the aldehyde or the ketone. Now folks, we have, this is acetal hydrolysis. So obviously you're starting with an acetal and you're doing something to it. The end of that word lysis, what does that mean? From biology, you guys know.
Split it?
Yeah, split it or break it. So we're gonna be splitting it somehow here. And then the hydro portion of it,
Water?
yes, water. So in chemistry, sometimes when we have the hydro prefix, we're meaning hydrogen, and sometimes we mean water. Right here, it's telling you you've got water. So we're using water and an acid catalyst to break up our acetal, and what do we get? Well, it's the reverse reaction of what we just did. You're getting an aldehydrate ketone plus a couple of alcohols. Exactly the backwards reaction. So, if we look at this right here, you can see that the ORs, you're seeing them over there and they're picking up a hydrogen. Where does the hydrogen come from? Oh, I thought I had a mechanism in here for you guys. I'll have to bring that with us next time. So you can see exactly where all the oxygens and hydrogens are coming from and going to, but I wouldn't expect you to know that. I would just give you guys the visual on it. Like usual, when I'm like, if you take Chem 12, you have to know this, but us, we don't. Okay, so it tells you right here where your bonds are breaking and that you are forming a carbonyl right here. So that's your carbonyl group. And you get your alcohol back over here. Now, the next thing we always do after we learn a general formula for something is we do problems. And that's what I have for you folks. We've got some problems. Okay, so we've got a little cyclic structure there. And I know you guys are all like, no, don't make me do that. But let's just go ahead and draw in the carbon that's bonded to the 2 ORs. And remember that that is OR right there. And what does mean? It's methyl. And if ethyl is CH2, CH3, methyl is what? It's a CH3. You guys remember that? The methyl group is CH3? Kind of, sort of, maybe? Okay, well, there you go. All right, so looking at the H3O plus right here. What is that? Yep, that's your acid catalyst. Okay, notice how you don't see any water here. You see that? The thing is with this, we imagine that we have this sitting in a ton of this. So this is another one of those things where chemists just expect you to know that if you've got acid there, it's sitting in water. So this reaction is happening in water. When it's on a test, I will try my very best to pick equations that show you the water. So you're not having to imagine or guess what's there too much. Because this is 2B, and we are learning, but I just wanted you to know chemists are lazy a lot of times and just expect people to know things when they don't. Okay, so in order to write the product, what are we gonna draw that's not changing?
Oh, yeah.
The cyclobutane, the box. So we go ahead and draw that. And that green carbon right there. If you do hydrolysis on it, what we saw back here is you took your ORs off and then you remade your carbonyl. Are we okay with that, folks? Okay, so that's exactly what we're gonna do right here. We're gonna do carbon double bond oxygen. Are we okay with what we did there and how it followed exactly the problem that we saw right here on this slide? Are we okay with that, you guys?
Yes.
So we're going backwards.
Yes, we are going backwards. Okay, so the other product, folks, is going to include the O-me's, so the ORs. But it's not just OR, it's what?
CH3.
You guys see how it's right there? When the ORs come off of the acetal, they pick up a hydrogen to become HOR or ROH, same thing. So what we would draw there is we would know that we would have two ROHs, but if we specifically know what R is, we want to draw that in. So you guys would put 2 CH3OH, or you could put 2 HOCH3, either way, because both of those are methanol, CH3OH or HOCH3. Are we okay with this, folks?
Yes.
Okay, all right. So just another aside, strange things in chemistry. You notice how we write CH3OH, but these hydrogens are together and then this one's off by itself right here. And sometimes it's like, why don't you just put CH4O? Well, you could do that, but this is a condensed formula, and so it's giving you a clue to the structure here. And what it's saying is that the single hydrogen by itself is somehow different from the other hydrogens. And why that is evident when you draw out the full structural formula, like that. And this hydrogen is indeed chemically different from these hydrogens over here. Oxygen will give up its hydrogen. Carbon will not give up its hydrogens. Carbon loves those hydrogens, is like, ooh, you're mine. Whereas oxygen's like, oh, okay, I'm done with you for a while. And a hydrogen will pop on and off right there. Is that clear, folks? Why we separated it out? Just kind of make that distinction of this is the alcohol hydrogen rather than the alkyl hydrogens. Okay, questions for me before we do the last problem? We're good? There's places in Riverside that sell marijuana.
Well, they were actually illegal here until they legalized.
I thought you were gonna say opium brownies. I'm like, wow.
No, I mean, but
Don't worry about what's going on back here. Just know I'm chilling really hard.
Okay. Alright, folks, we've got this weird little beast here, but we can do it because we learned how to do this one. Okay, so do we kind of sort of see that we might have an acetal there, but it's like weird?
Yeah.
Okay, plus we're in the acetal hemiacetal section, plus we just did an acetal problem, right? So it's probably the same thing, right folks? Okay, so let me go ahead and draw in the carbon that we need to identify. Now notice over here, we have OR. Do you guys see that one? That's the easy OR to identify. And that one is O and you've got CH3 or H3C. Either way, that's what that is there. Are we all right with that? Okay, so on the other side, if we're drawing our products, we know that we go ahead and reinstate the carbonyl carbon, and we're gonna have to have two alcohols. Now the alcohols can be the same or they can be different. So if you had a solution that had a mix of ethanol and methanol and you reacted it with an aldehydrate ketone, both of those are gonna react there and you might get an acetal that has OMe and OET, different ORs on it. Okay, so I'm gonna go ahead and write in one of our alcohol products, and that came from this right here, and when it hops off of the acetal, it picks up the hydrogen to become the alcohol. Are we okay with that part of the product? Okay. Now, the other side over here, can you guys see how this is also OR? So we've got OR and we've got OR here. Are we okay with that? Okay. The problem for us is it's connected on the back side, and so we're like, oh, I don't like that, I don't like that. So put your hand over it, and then you can see OR and OR, right folks? Okay, so what are we gonna do with this? Because we can't just simply write an alcohol, because this alcohol right here is going to include the rest of all this up here. So we kind of sort of have to be careful with this one. This type of one would probably not appear on the exam because it's kind of like, oh, what do I do with that, right? But it's fun to do these ones. Okay, so what's gonna happen is the carbon that was connected to both of the ORs, we know that that's gonna go back to the carbonyl carbon. Are we okay with that?
Yes.
Okay. Now, this over here, CH2, CH3, that's gonna stay connected to that blue carbon. And I'm gonna draw it off to the side like this. And nothing happens to it, it stays. Are we all right with that? Okay. So I'm going to finish drawing the rest of the R group right here. And you can see that we've got 1, 2, 3, 4 carbons that are bonded to that blue carbon there. So the first one right here is there. And this is not any kind of official numbering or anything like that. I was just writing this so you guys can see how it corresponds. Are we okay with that? Okay, and then right here, this 4th carbon here is connected to what?
Oxygen.
The oxygen right there. And let me write that oxygen in black. So we've got O right there. But when we do hydrolysis, we're taking the ORs off, like pulling them off, and they're gonna turn into, instead of RO or OR, into what? They're gonna pick up a hydrogen, folks, because you don't wanna have an oxygen just sitting there because you're in acid. So if you're in acid, you have H pluses just floating around all over the place, so it hops onto that oxygen right there. And now you have your ketone portion, so you have one of your ROHs, and now you have your ketone, but what happens is that the other ROH is connected to your ketone because you started with this ring here. Ah, right?
Yes.
Okay, so I understand, yes, rings freak us out, but woo, this one opened up. Okay, folks, I was going to start the next chapter today, but then I looked on the schedule and I scheduled it for 2 weeks, and I think I can get through it all with some spare time even. So I'm not gonna push ahead. I think I'm gonna let you guys just go do your exam or study for your exam or whatever, because I think this topic right here has a lot of components and it's a little bit weird, so I don't want to keep going, okay? Has anyone done the exam already?
No.
Not
I'm gonna do it
yet.
after the lab.
Okay, yeah, no problem, so until 11:59. Okay, questions from me before we get out of here? Yes, sir.
For this one, as you mentioned, so the oxygen, there's no connection to the oxygen, just the hydrogen. Is there a
Are we talking about the black oxygen?
no, the blue one is with
Oh, the carbonyl oxygen right here?
yeah.
Yeah, that's just
Right.
connected, double bonded to a carbon. It has 2 lone pairs on it that I didn't draw in, but I just expect you know where they're, because I'm a chemist. Any other questions, folks? All right, good luck on the exam. Please don't wait until 10 p.m. because you know that's when your Wi-Fi goes out and you forgot to get a hotspot like I bugged you to do, and then you get mad at me.
No worries, I'm paying the bill.
Okay.
Or I'll find another service.
All right. Monday's lecture, folks. Just right before I came in here, it said, "Oh, it's done." So it's there in case you need it. What? 21. It's esters. Oh, we're making esters. So we're making banana oil and wintergreen. It's a fun lab.
You want to have a scientific joke?
Yes.
Why can an acid not form a relation with another acid?
Why?
Because they wind up splitting apart. You get the point that atoms can split. And so I thought that's why I who's not a chemist, I was like, why can't an atom split not form a bond with another atom? Because they always split. So it's like, I get it. You never take chemistry yet in the morning. I'm like, you're gonna need to learn that because what if you put something in your skin? And they change the names.
Yeah.
I need to find a mattress. They're expensive.
Yes.
Do you by any chance have back problems with something?
A little bit, but not a whole lot.
My parents, to be honest, are cheap freaks. They're like, why are you wasting money on a good mattress? I can get you one from a warehouse. I'm like, which is where, man? Dark alley?
Oh no, good mattress is worth every penny.
Oh,
Absolutely.
speaking of which, I actually have the business card for the mattress. It's called Sit and Sleep.
Oh right, yeah. I
They
heard
I found out that my specialty mattress is the blue sheet. There's 3 of them, red, green, and blue.
Alright.
I'll see you over there.
In lab?
Yes.
Okay, I'll see you in lab.